So this one has to do with gravitation. Gravitational force of attraction between Santa and Mrs. Claus is some force F when they are a distance r apart from one another. So let's write out Newton's law of gravitation. So F, you can put Fg if you want, but I said it was F. So that's going to be equal to G times the mass of Santa and the mass of Mrs. Claus. I wonder what her first name is. Santa and Mrs. Claus. Okay. All over some, what did I say, distance d? Oh, distance r. Okay, all over r squared. That's, Newton's law of gravitation. Fg equals g m1 m2 all over r squared. All right, there's a negative sign technically in the equation, but that's not important. It just means that it's an attractive force. It's always attractive as far as we know. So, what will happen to the gravitational force of attraction between them if Santa triples his mass? Too much fruitcake. I'm laughing at my own jokes. I'm sorry. So right now, they're a distance r apart. There's their masses, and there's the force between them. But suddenly, he has way too much fruitcake, and this goes up to 3. Notice that the force is directly proportional to each individual mass. And so if you triple just one of the masses, you triple the force. They're directly proportional. If you tripled both of them, Mrs. Claus, stop eating all that fruitcake. Who wants fruit? I'm sorry. If you like fruitcake, I apologize. If they both tripled their masses, then it would be 3 times 3 would be 9 times greater. But if only one of them triples it, all right, then, if the other ones remain constant, and that's the only one that varies, you triple the one that's only the triples, and that's going to triple. Okay, this is directly proportional to each individual mass. It's directly proportional to the product of the two masses, but if the other one doesn't change. So if you triple that, you triple that. If you were to double his mass, you double that. If you were to quadruple the mass, you quadruple that. They're directly proportional. What will happen to the gravitational force of attraction between them if the distance of separation between them triples? That's down here. They get further apart, right? They were here, so there's some distance r. And now they're, that's a little too far. They're like here, so now there's this distance 3r. They have the same masses though, don't change their masses. Well, if you put 3r down here and square it, that's 3 squared is 9 in the denominator, so you would have 1/9 the original force. So the further away you get, the lower the gravity. All right, gravity decreases the further away you get from something. If they were 4 times further away, it'd be 1/16. If they were twice as far away from the original, it would be 1/4. All right, you're squaring whatever you do to the distance, but it's in the denominator. Okay, that was fun. To find the concept of inertia, I actually did that earlier, but an object at rest tends to stay at rest, an object in motion continue constantly in a straight line. It's a resistance to a change in an object's motion. It's measured by an object's mass. The greater the mass, the greater the inertia. Can you have inertia when you're at rest? Yeah, right, because it's just a measure of an object's, mass is a measure of an object's inertia, and you have mass even when you're at rest. If something is weightless, can it still have mass? Yeah, of course. Right? Mass is a measure of inertia. It's not a force. A force of gravity, weight, is obviously gravitational force pulling on a mass. So you can be up in the International Space Station where you are effectively weightless, even though you're not truly weightless. You can be effectively weightless and still have mass. You bump into something, it can still hurt. You can be way out in outer space where gravitational force is really small, not measurable, it's so small. You still have mass. It's a measure of your inertia. Measure the amount of matter that makes you, you. A ball is traveling horizontally when you catch it. Ouch! That hurt your hand. Is this an example of inertia in action? That's in parentheses, think mass or weight. I actually explain this in a different part of this. It's net force equals mass times acceleration. Right? Your hand, you're catching something that you're applying the force to decelerate the mass. It's got everything to do with mass. And for the AP folks, you really have to understand the difference between what we call inertial mass, which is your hand decelerating the mass of the object, versus weight, which could be like your hand just holding an object's weight. They actually are technically different, although there's no inertial mass and gravitational mass. There's no way to tell the difference. But it's one of those weird things. But you can hold something that has weight, right? M times g, although it's not accelerating. M times g, even though it's not accelerating with 9.8 meters per second squared, but its weight is m times g. You can hold it. That's its gravitational mass, the Earth pulling down on it, with acceleration of g, even though it's not accelerating. Or you can stop something with your hand that's moving, catch a ball. That's called inertial mass because you're stopping it with your hand. That's a subtle point that's not that important. Going back to the original thing, would it hurt if you catch it? Yeah, that has everything to do with its inertia because you had to apply a force to stop the ball. That has to do with inertia, not weight. It has to do with mass, not weight. Okay. Again, going back to this is net force equals mass times acceleration, not weight times acceleration. All right? It's mass times acceleration. It has to do with inertia, mass. Okay. Where are we? If a ball is traveling, I already did that one. Describe how orbit works. Why do astronauts feel weightless while in orbit, even when there is quite a bit of gravity acting on them? So if you're up in the International Space Station, the gravitational force acting on you is only about 10% less than the gravitational force right here in my classroom. And let me get something to throw. No, I'll just, if you throw something. Isaac Newton, I talked about this in class, at least I hope I did. Isaac Newton actually drew this picture. Here's the Earth, and you have some massive mountain on it. And you launch a ball from the top of the mountain, and it follows projectile motion. Plunk. No great surprise, right? Now, so let's throw it a little harder. Boom, plunk. Okay? It's just projectile motion. But what if you launched it so fast? This is the Earth again, all right? Earth. What if you launched it so fast that it's going to curve away? You know, there's no Earth anymore. This thing has so much projectile motion, so much horizontal velocity, that by the time it hits the ground, there's no ground anymore. It's trying to hit the ground because it's moving with horizontal velocity and vertical velocity. Notice it was here. Now it's here. All right? If you didn't give it horizontal velocity, it would have fallen straight down and hit the Earth. But it's falling down and moving horizontally. But it has enough horizontal velocity that its range is bigger than the radius of the Earth. So it's trying to hit the Earth. It's falling, but it's got so much horizontal velocity, it just keeps missing the Earth. All right? That's orbit. Okay? Orbit is something where everything's in free fall. Everything's in free fall, but they have enough horizontal velocity to keep missing the Earth. If you were on an elevator and the cable snapped, God forbid, you're going to be fine for whatever reason. All right? Clarence the angel is going to come and buoy you up just before you hit the ground. But you're falling in an elevator in free fall. As the elevator's falling, accelerating at negative g, you're in it, falling at negative g, and while you're falling, you could float around. Because everything's falling next to each other. Everything's falling together. That's what's happening in the International Space Station. Everything's falling together with the exact same rate of acceleration downwards and the same horizontal velocity together. Everything's moving together. So you're all moving with the exact same motion. Vertical free fall and horizontal, same horizontal speed. That's orbit. Okay, everything in orbit's doing the same thing. So you could be inside the spacecraft and floating around, or you could be outside the spacecraft, right? And you're moving horizontally with the same speed as the spacecraft and falling with the same speed as the spacecraft. If you want to deorbit something, then slow it down, and eventually it's going to spiral in and crash. You just have to slow it down just a little bit, and it'll spiral and hit the Earth. But as long as it has enough horizontal velocity, and it needs a very specific horizontal velocity to stay in orbit there, it'll be just fine. That's what is so classic about that movie Gravity, when they're moving neck and neck, and Julia Roberts has George Clooney's hand. I got you. Oh, you let go. No, I can't let go. They're moving at the exact same velocity in orbit together. She lets go. He'd stay right there. There's nothing. I got the exact. Oh. Anyhow, that's how orbit works. What variables affect the orbital velocity of a satellite? That equation, let's just assume that it's circular motion. I have to be sure I don't overdo the time here. So if you take this equation, g m1 m2 all over r squared, and this is going in a circle, and so this is the centripetal force, and this is going to be, for example, the mass of the Earth, and this is the mass of the satellite. And then it's the satellite going in a circle. So the satellite, remember the centripetal force equation? The centripetal force equation is mv squared over r, okay? And so this is the satellite that's going in a circle, and so this is going to be the centripetal force equation. Okay, why centripetal force? It's circular motion. Where does the circular motion come from? Or that's the equation for circular motion, mv squared over r, mass times centripetal acceleration. Where does that come from? It comes from gravity. This is the equation for gravity. Look at the one thing that cancels out here is that, the mass of the satellite. You also lose one of the r's, okay? So you get the fact that the velocity, the speed squared of the satellite equals big G, the gravitational constant, times the mass of the Earth in this case, the mass of whatever is being orbited, divided by r. You take the square root of that, and it's G me over r. Those are the things that affect the speed of the thing in orbit, is the mass of the thing being orbited, and the altitude, basically how far away from the r is from the center of the planet or star or whatever being orbited. But basically, it's the greater the mass, the faster you have to be going to stay in orbit. The greater the mass of the thing being orbited, in this case the Earth, the satellite has to be moving faster. And the further away it is, the satellite's going to be moving slower. Right? So the further out you go, the slower it travels to stay in orbit. Okay, because it's inversely proportional to the square root of r. How are we doing on time? Okay. All right, I'm going to stop this one. Wait a second, hold on. Compare the centrifugal force and centripetal force. Whereas centripetal force is the direction of any force inwards on a circle. All right, that's called center seeking. When I had the tennis ball on a string, woo, that was tension that was centripetal, pulling in on the ball. It's the inward force. The satellite in orbit about a planet, gravitation is the centripetal force. You going around a corner in your car, friction is the centripetal force. That's centripetal with a P. Centrifugal with an F, it does not exist. Remember, that's a force pulling something outwards. It does not exist. There's no such thing. What people are confusing centrifugal force with is this idea of inertia, okay? The tendency of objects to go in a straight line, and that's why they end up on the outside of the circle.